Hello, Dr. Ken here, and for today's lab, we will be going over the scientific method. All right, science is an active process, not merely a collection of facts and unrelated information. And the scientific method is a method of research with defined steps that include experiments and careful observations that are used to investigate a natural occurrence. So the scientific process starts with an observation and a question. So let's go over an example. Suppose you're in a home improvement store and you notice a bag of fertilizer. Dr. Ken's fertilizer, best fertilizer available for flowers. And you wonder, is this fertilizer better than the fertilizer I currently use for the flowers in my garden? So you've observed the fertilizer, and now you're asking a question, is this fertilizer better than my current fertilizer? So the next step is formulating a hypothesis. A hypothesis is an educated guess based on observations to predict the answer for a problem or question. Okay, and a hypothesis must be falsifiable, meaning that you can perform a test on the hypothesis, and based on the results of that test, they can either falsify the hypothesis or support the hypothesis. We call that falsifiable. The hypothesis must be falsifiable. A hypothesis is never really proven to be true with absolute certainty, but if there's a lot of experiments that support the hypothesis, then we can make an assumption that the hypothesis is true. Okay, so we see a bag of fertilizer in the home improvement store, and it says the best fertilizer available for flowers. So based on this information, we can formulate a hypothesis. So an example hypothesis would be, if I use Dr. Ken's fertilizer, my flowers will grow better than my current fertilizer. Right? The null hypothesis is a prediction of what would happen if the experimental condition has no effect. There's no dependence between the prediction and the outcome. So in our example, the null hypothesis would be, if I use Dr. Ken's fertilizer, my flowers will not grow better than my current fertilizer. And note that the null hypothesis is not the opposite of the hypothesis. For example, the opposite of our hypothesis will be Dr. Ken's fertilizer will kill my flowers, or Dr. Ken's fertilizer will make my flowers grow poorly. Okay, that's not the null hypothesis. That's a different hypothesis. Okay, so next we make a prediction. A prediction would be what we expect to happen if the hypothesis is true. In this case, we predict that the flower plants will grow better with Dr. Ken's fertilizer than the flower plants grown with the current fertilizer. Okay. Next, we have to set up an experiment. An experiment is a scientific procedure to test a hypothesis, and the results will either support or refute the hypothesis. Okay. Now, the outcome of the experiment must be measurable, and in an experiment, there are variables. A variable is anything that can change within an experiment, and there are three major types. We have the independent variable, the dependent variable, and the standardized or controlled variables. Okay? So the independent variable is a variable that you intentionally change during the experiment. In this case, the independent variable is whether or not you use Dr. Ken's fertilizer. The dependent variable is the variable that may change as a result of changes made in the independent variable. This is the variable that we are observing to see if it depends on the independent variable. Okay, so in this case, the dependent variable is how well the flowers grow. And then we have controlled and standardized variables. These are variables that must be kept constant between the controls and experimental samples. Otherwise, they may affect the results. In this case, our control plants and our experimental plants must be grown under the same conditions, such as the same soil, same amount of sunlight, same amount of water. Okay. Next we have the subjects. In an experiment, you have experimental subjects and control subjects. The experimental subject is the subject where treatment is applied. So in this case, we're going to be using flower plants. So the experimental plant will be the flower plants that are treated with Dr. Ken's fertilizer. And then we have control subjects. These are subjects that are not exposed to experimental treatment. So, our control plants will not be using Dr. Ken's fertilizer. We have positive controls and negative controls. A positive control subject is a subject that you know will have a favorable outcome, and a negative control subject is one that will not have a favorable outcome. So in this case, for the positive control, we'll use a flower plant. We'll plant a flower plant using our current fertilizer. Okay. We've used this fertilizer in the past. We know it works well. We expect the plant to grow well. And for our negative control, we'll use a flower plant that does not have any fertilizer. And we expect the negative control not to grow very well. Okay. Okay, so here is the experimental setup. We'll plant 3 flower plants without fertilizer. That will be our negative control. And we'll plant 3 flower plants with our old fertilizer. That's our positive control. We expect them to grow well. And then we'll plant 3 flower plants using Dr. Ken's fertilizer. Okay, so these control subjects are necessary as a standard of comparison against the experimental subjects. They give us something to compare to so we know how the experimental subjects fare against the controls. And there's also standardized or controlled variables such as the same amount of sunlight, same amount of water, same soil quality, etc. If these are not kept constant amongst all 3 groups, we may get misleading results. So for instance, if the no fertilizer and the old fertilizer didn't receive the same amount of water as Dr. Ken's fertilizer, as the plants with Dr. Ken's fertilizer, the plants using Dr. Ken's fertilizer may grow better, but that's not because of the fertilizer. That could be because we gave it more water. So these control variables must be maintained constant amongst all 3 groups. Okay, next we have data collection and results. After 3 months, you notice the plants using Dr. Ken's fertilizer are healthy and have more flowers than the old fertilizer. Okay, so here are the results. The plants with no fertilizer, they didn't produce any flowers. The plants with the old fertilizer produced lots of flowers like we expected, but Dr. Ken's fertilizer produced a ton of flowers, more flowers than the old fertilizer. So now we can draw our conclusions. Flower plants grew better using Dr. Ken's fertilizer than the flower plants that did not have any fertilizer or used the old fertilizer. So we can draw the conclusion that Dr. Ken's fertilizer works better than the old fertilizer, and our hypothesis is supported. So here's a flow chart summarizing the steps involved in the scientific method. We start with an observation. So we saw a bag of fertilizer in the home improvement store. We ask a question, will this fertilizer work better? Then we form a hypothesis. If I use this new fertilizer, my flowers will grow better. And then we make a prediction based on the hypothesis. Using the fertilizer will make my flowers grow better. And then we perform an experiment to test our hypothesis. So we set up our control plants, positive and negative controls, and then our experimental plants, and using the new fertilizer, and we observe what happens. Okay, and then we analyze the results. In this case, the plants using Dr. Ken's fertilizer grew better, and our hypothesis is supported. So now we can publish our results, report our results in a peer-reviewed journal so that other people can, review our data. Okay, so today we will go over a real-life application of the scientific method. So distractions by cell phones cause accidents. So the National Safety Council reports that cell phone use while driving leads to 1.6 million crashes per year. Nearly 390,000 injuries occur each year from accidents caused by texting and driving, and 1 out of every 4 accidents is caused by texting and driving. Okay, so in this lab we will design an experiment that measures the effects of distractions on reaction time. Okay, slower reaction times result in more accidents. All right, so we will do a reaction time experiment. Now that you know how the scientific method works, let's measure reaction time by measuring the distance a ruler falls before being caught. Okay, so you're going to need to find a partner to work with. You'll work in pairs. One person holds the ruler from one edge and drops it while the other person tries to catch it in one hand. So you'll have a ruler here. One person will be dropping it. The other person will be catching it. And do it a few times to get the feel for it before we actually start the experiment. And you're going to do it 10 times without a distraction and 10 times with a distraction. And the distance, how far the ruler falls, will be a measurement of your reaction time. Okay, so hold your thumb and index finger about 3 inches apart. Have your partner hold the ruler right above where your fingers are, and have your partner drop the ruler, and then you'll close your fingers and catch it, and then you'll see how far the ruler fell by the time you caught it. It's best to measure it in centimeters. Make sure you have the lowest centimeter at the bottom where you're dropping it. So the larger the number, the larger the distance it drops, the larger the number of centimeters. So if you look here, I caught it at 15 centimeters. Okay, if the ruler drops and falls all the way through, record that as 33 centimeters. Okay, don't record that as 0 because a recording of 0 means you caught it right here. No, if it falls all the way through, record it as 33 centimeters and put a star next to it so I know that it fell through. Right? So you have to come up with hypotheses that would happen to reaction time if a distraction is applied to the catcher. You get to choose your own distractions. So for instance, let's say counting back, saying the alphabet backwards. Okay, let's say that's your distraction. Okay, that will be your independent variable, whether or not you're reciting the alphabet backwards. The dependent variable is how far the ruler drops before you catch it. Okay, that is what you're measuring. And standardized variables will be things like using the same ruler, performing the experiments at the same time of day. You don't want to do the control run in the morning and then the experimental run in the evening, and you want to do this in the same environment. Those are all standardized variables. All right. So what you'll do is you'll do 10 ruler drops without any distractions, and then you'll do 10 ruler drops with the distraction that you chose. So reciting the alphabet backwards, Z, Y, X, W, V, U, etc. And then while I'm saying it, the dropper will drop the ruler and I'll have to catch it. And then we will record the results. We'll do two different distractions, treatment 1, treatment 2, and then our control with no distraction. Okay, make sure the catcher and dropper of the ruler are the same in the control treatment as well as the experimental treatment. You don't want a young kid doing the control runs and then have someone else, your grandfather, do the experimental run. You know, different people have different reaction times, so the catcher and dropper must be the same throughout the experiment. That's a controlled variable. Apply the distraction to the catcher while the ruler is being dropped. Perform 10 drops without the distraction, 10 drops with the distraction. If the ruler falls all the way through, record that as 33 centimeters, and then calculate the mean and standard deviation. Okay, so and then repeat the experiment using the other distraction. Okay, and then you'll record your data on a spreadsheet and you'll calculate the mean and standard deviation. Okay, the standard deviation is a measure of how spread out your data is, how dispersed it is, and this gives you an idea of the repeatability of your results. Okay, and then you will draw your conclusions. Did the distractions support or reject your hypothesis? And what other experiments can also be performed? Okay, so next let's go over how to do the human benchmark reaction time test. To get to the human benchmark, open up a browser and type humanbenchmark.com in the address bar, hit enter, and that should bring you to the human benchmark website. Click the get started to begin the experiment, and then the screen turns blue. Click anywhere in this blue area and the screen will turn red. As soon as it turns green, you click your mouse button, okay, and it will record the time it took for you to react. In this case, it was 418 milliseconds. And then I can do it again. I click, wait for green, and as soon as it turns green, I click again. This time it was 359 milliseconds. Okay, so you're going to do this, do it a few times to get some practice on become familiar with the test. And once you're familiar with it, do 10 clicks without any distraction, and then do 10 clicks with a distraction and record your reaction time for each of the clicks, and then calculate the mean and standard deviation, and you can determine whether the distraction slows down your reaction time. All right, thank you for watching. I will see you guys next time.